This is about transient entities. All right, so what's that about? All of our models, or almost all of our models so far, have been counting things. You know, our canonical model, the multiple server queue, has counted the number in the queue, counted the number of available servers, and that, as I mentioned, is very efficient. It's extremely fast. The downside is that there are things that can't completely be represented. I showed an example of how to use a container and save the arrival times, the SIM times of the arriving customers, and then use those to explicitly compute things like the delay in the queue and the time in the system. Those are quantities that we're definitely interested in a system like that, and similar systems. That is, how much time do we spend you're just sitting around waiting? The thing about queue times, and I hope that this is one of the takeaways from just looking at this whole class of models, is that the facilities like this, situations where you get processed, are, first of all, they're all over the place. I mean, as soon as you become aware of these models, I hope that you're noticing that almost everywhere you go, there's some kind of queuing system going on. And the thing about these is that there are typically two parts. One part is unavoidable. What's unavoidable is the amount of time that it takes to get processed. So whether I'm going to the DMV or to the supermarket or to the bank, or if I'm a shop that manufactures things, or if I'm a repair shop that repairs things, if it takes a certain amount of time to perform a task, the task at hand, you know, so whether it's processing at a given station in the DMZ, a certain amount of time to check out the groceries at the supermarket, a certain amount of time to do the transactions at the bank, that's kind of a given. That's something where if it takes this long to perform this task, then that's how long it takes. So where can efficiencies typically be squeezed out of the system? And those are in the places where that are basically waste. And so if you're a customer and you're waiting in line, the chances are, if you're like most people, at some point you get kind of annoyed. And that's really natural, because when you're waiting in line, you're not making any progress towards your goal. You're not making any, nobody's working on you. So whether you're standing in line at the bank waiting for your turn, or whether you're on hold and your call is very important to us while you listen to elevator music, either way, it's like nobody knows about you. They're not working on your problem. And that's all just waste. So the amount of time that we spend in the queue is an important measure in so many situations, because that's usually the place where we can try to squeeze some efficiency out of it. The problem with our models that just do the counts, like number in queue and number of available servers, well, specifically number in queue, is that they weren't representing the actual customers. And what we saw with when we succeeded in computing the expected average delay in the queue and the time in the system, was that we had to kind of save the time and keep those in a queue, in a FIFO container. So those times, those numbers represented each individual customer. So for the first time, we were actually representing the individuals. And then yesterday, we saw an example of this reneging idea, the idea that when we observe our system, at some point, the customer gets impatient and then leaves. And there we represented each customer as this unique ID, just this number. And then I pointed out that, well, okay, that's fine, but what if we wanted to get the things like the delay in the queue and the time in the system in that model. So in that model, as it was given, we didn't have the capability of doing that because we weren't able to save them. Now, we could have added another variable and had another container that would hold those. But it turns out that there's actually a more effective way. And that's where we get to these transient entities. So what are these transient entities? These are objects that represent these individual things in the system. And I say things in the system, not to dehumanize anyone, but many times the things are things like jobs, or it might be the chassis and the rotary and the electronics of a particular vehicle. So maybe the things may be things, they may be people, whatever. So what these transient entities do, and what I hope one of the takeaways you had from the Java class in terms of object orienting, is that we can, with objects, we can bundle together a bunch of attributes. And those attributes can kind of carry along with them information that we are interested in. So in this particular case, the attributes that we're interested in have to do with what's going on with our customers. So the things that we'd be interested in, well, actually, name is one thing it actually doesn't have to do with the direct impact of the model, but it's kind of a convenient thing to, especially when we're debugging, to know what these things are, to give them each a name. But in general, keeping in mind what we were doing in that model where we were saving the time, there are two quantities that we'd be interested in. One is the creation time. That is, when did this thing get, quote, created? And then there's that's a fixed quantity. So it's like if I get created at a certain time, then at any point in time I can figure out what my age is. In other words, how long has it been since this thing got created? If we're modeling things like items that have a certain shelf life, then that might be another attribute. And then the age of our object would be something that we would be interested in. So if we knew when we were created, basically the birthday of this entity, and we knew what time it is now, then I can always figure out what the age is. And these entities have no shame. They don't care if you know what their age is. Now, another thing is that, and this kind of corresponds roughly to what we were doing when we were computing the delays in the queue, is that it's useful to have what I call a timestamp. So a timestamp is just, I'm going to mark the time when a particular event occurs, and I'm just going to save that. And if I have that, then I can figure out what the elapsed time is at any time in the future. So how might I use that? Well, if one of these entities, if you just think about this, and we'll see this in a little bit with the model and with the code. When I show up at my system, if I stamp the time, and then sometime later I'm in, I've started service, then the elapsed time since when I stamped it showing up and when I started service, that's the delay in the queue. And if I have access to this entity when I finish service, like at the end service event, then I can figure out how long I've been in the system. And one image you can put in your mind is going to a parking garage. So you go into a parking garage, you get a ticket, and that ticket is time-stamped to when you come in. And then when you leave, you hand the ticket to the guy on the on the outside, if there is a guy there, and he kind of stamps it again, and then computes the difference between the current time and when the original timestamp was. That's the elapsed time. That's how long you were in the parking garage, so they know how many hours to charge you. Okay, so that concept is what we're going to be using here. So the methods that we have are, well, one would be stamp time. And what that does is that sets the timestamp to the current value of sim time. And then get elapsed time will return what sim time is minus the timestamp. Okay, so, and again, not rocket science, but it's something that's very useful. So a simplified UML class diagram for this. You all remember these UML class diagrams. See, this is not, these entities are not the same as sim entities. Sim entities are things that can schedule events and put them on the event list and process them. Entities are a bit more passive objects. They can't schedule events or do stuff like that. But these are, entity actually has a little bit more than this, but these are kind of the key things. So we see that their attributes include things like a unique ID, a name. Again, that's something. These two are not necessarily germane to what we do. The creation time, again, this is not some sort of magic. You know, how do I remember a creation time for an object? I have it as an instance variable, or attribute is kind of the common name. And then here's the timestamp, which is something which every time I stamp the time, that gets saved. If I say get elapsed time, that will return the current time minus the timestamp. So that'll tell me how long has it been since you stamped the time. Okay, in SimKit, there is a class, and of all things, it's called entity, and it has these characteristics. And so that's something that we can use. So now what we're going to do is we're going to take these entities and we're going to use them in our server. So in this way, we can capture almost anything that is possible. So for our entity server component, again, and notice I said, because I said component, we're not going to worry about the arrivals. Now we have to worry a little bit about the arrivals, as we will see, but we've already done this several times, so that should be, I think you can imagine what we're going to do on that. Okay, so our parameters, again, the number of servers, total number, and then the service times. Again, a sequence of times that we're going to use. Typically in the implementation, these are going to be random variates. Likewise, our state variables are number of available servers, initially K. And now our container is going to contain entities. So before we had a container that had times, yesterday we had a container that had integer IDs, but now this container contains the entities, and it has all that information that we want. And then finally, because these are the things we're kind of interested in estimating, we have the delay in the queue and the time in the system. So those are state variables of our server component. So this structure should look fairly familiar. We've seen this pattern many, many times. This is really the basic server pattern. We've seen that starting with our simple server, actually starting with our multiple server queue model, and then noticing that this pattern right here of these three events that have this relationship kind of stood out as one thing. And so our simple server component then just had that. And we've seen several different variants of this, like the one that explicitly calculated the delay in the queue, the one yesterday that had the reneges as well. And then we also saw something very similar in that disassembly model, where if we looked at it very carefully, we saw several embedded patterns like this. So again, while it is useful to identify the patterns, as we saw in the machine repair model, and as I hope you saw in the machine repair model that I asked you to do for the last written assignment, that the way these things work is not, it's not just sort of boilerplated to this. That is, sometimes you might have an edge that goes somewhere else, or sometimes you may not even have one of these. As we saw with the blocking model, it turns out that the end service in the first one couldn't directly schedule another start service. It had to go through another event. So that was something different. But again, this kind of pattern is something to recognize, but not just sort of blindly follow. Okay, so how does this work? So we have, first we initialize our state variables. And again, this, when you're doing one of these, you can always, if you take the care to define your state variables fully with the initial values, then you can always write down the run event. Just as an aside, if there are no state, if you don't have any state variables, then you don't need a run event. Well, you don't need a run event if it's also not scheduling anything. Okay, remember this run event doesn't schedule anything because the idea is that this arrival event is going to have to be hearing it from some other component that's generating it. Okay, so let's look at.
I got a question on that.
Sure.
Well, I mean, you say that, but when are you expecting us to draw all these graphs out for the other component, and when is it? Can we write it simply where it is here, where it has run, and the run here almost implies that something else happened and filled all the E's.
Right.
Yeah.
Yeah. So great question. Thanks for clarifying that. The expectation is that if you do a component like this, and actually in most of the ones coming up, I'm going to ask you just to do a component. You should also have a listener diagram that says how you're going to be, how it's going to be driven. In other words, if it's only a component, you need to say, okay, how is this actually going to be run? And the answer is going to be some diagram that looks like this, where I say, okay, here's this component is going to be producing the events that are going to trigger this component. Okay, does that answer the question?
Mm-hmm.
Yeah. Okay, and as you saw, we're gonna get to that in a second. So, but let's first, just go through and just see what's going on here. So this is similar to a lot of the models that we've been doing, but it has a slight difference. So for just right at the arrival event. So the idea is that the arrival event has as its argument one of these entities. So this arrival event, the argument is going to be an entity. And so the first thing we need to do is we're going to stamp the time and then add it to the queue. And the thing is, you need to stamp the time before you add it to the queue. And the reason for that, it has to do with the comparator that these things use. I don't necessarily want to get all the way into the weeds, but the first, the entities are comparable. And their rule is first sort based on stamp time, or the time stamp. And then the secondary one has to do with its unique ID. That is, every entity has a unique ID. And so that's the secondary comparator. But again, we stamp the time and then we add it to the queue. And keeping in mind what happens in the SimKit piece, then we're going to fire a property change that's going to notify some listener that might be interested, typically a statistics object, that will say this state variable has changed. Okay, so now if there's an available server, we're going to schedule a start service with a high priority. Okay, we've seen that before. And now, okay, QPOP is kind of the shorthand for what we're going to have to do. In the implementation, we're going to have to do it in 2 steps just because of a Java quirk. But what this does is, so when we pop something off the queue, its size has decreased by 1. So again, we would fire a property change after this. This is a state transition right here, state transition. And then we decrement the number of available servers. That we've done that before. And now our delay in queue is simply the elapsed time. That is the time between when this entity showed up at the arrival event and had its timestamp invoked. And the elapsed time now, which the entity itself does the computation for, see, now this is a little more safe and easy than before. If you remember, in the previous model, we had to take our sim time and subtract it from the value that we popped off. And again, that's not rocket science either, but that's more prone to errors than what this is. I simply say to the entity, how much elapsed time since your timestamp? And that is going to be the delay in the queue. And since this is a state transition, that will be fired as a property change. Then we take this guy we popped off, that's a local variable, and we pass it as an argument to our end service event. Again, it's absolutely important that there be a match between the parameter in the box and the event that's being scheduled. And if there is none, there can't be a box either. That's sort of the other thing. Again, the delay is the time, the service time. And then here now, because we have passed our entity as an argument, we now are able to get the elapsed time, which is the time. Okay, when was the timestamp given? It was back with the arrival. So the elapsed time is the time since between when they arrived and what the current time is, and that's the time that we've spent in the system. So notice that no other time did we stamp the time, and that's important here too. A critical thing is that every event has to have access to whatever computations it's doing. And what are the computations it's doing? State transitions and scheduling edges. So for every event that you do, look at it and say, how does this event know to perform this task? So how can it perform stamp time on E? How does it know what E is? Well, somebody told it. It was passed in. How do you get access to Q? How do you know what Q is? Q is a state variable, and all events have access to all state variables and all parameters. How does it know that it can add E? Because somebody told it. So in start service, now it's a little different. Now here, E is a local variable. So how does it know to pop off the top guy in Q? Again, Q is a state variable. Every event has access to every state variable, so it can perform this. So S is a state variable, it can perform that. Okay, D is a state variable, but what about E? Well, how does it know what E is? E is the one that you popped off here. Then see, now it schedules end service. Okay, it has the service time. How does it know the service time? The service time is a parameter. Every event has access to every parameter. Now here it's passing E. How does it know what this parameter E is? Again, that's the local variable that it popped off. Finally, end service. Okay, how does it know to execute this? S is a state variable, so it has access. How does it know what W is? Another state variable. How does it know to do this, this expression? How does it know what E is? Somebody told it. You passed it in. And again, the shorthand in the code, we're gonna have to say get elapsed time. So, but there's sort of short. And likewise, the empty is empty. So we'll see that in the code. Okay, so now you said, all right, since this is a component, it is important when you're writing just a component to say, okay, now how can this component get executed? Because in this case, it's not completely obvious because of the argument on the arrival. See now, anything that has an arrival or arrival-like event, we can derive with an arrival process. We've seen several examples of that. But if it has an argument, then the arrival process by itself is not sufficient for that. We need to do something else. And the pattern that we have two patterns. One is to kind of do it from scratch. So here's one example of an entity arrival process from scratch. So again, we schedule these arrival events that are going to keep occurring. And for each one, we're going to instantiate an entity and then pass it as an argument to an arrival event whose argument is an entity. What makes this arrival event match this arrival event is not the name of E, is not the name of the argument. It's the type of the argument. In other words, if I try to drive this, if I try to have this component listen to one of the other ones, like the one we did yesterday, where the arrival events had as their argument the ID, just that integer, then that's not going to work because an integer is not an entity. Okay, so, but this will, because the E that gets passed, the argument that gets passed is an entity, and that entity is going to be able to have its time stamped. Okay, so this is a one way to do that. And then the lazy way, which is one that I've been kind of advocating, is to take everything we've done with the arrival process and then just subclass it. So our entity, and this is what I've implemented in the code, which we'll look at in a second. So the entity arrival process, again, notice we're overriding the arrival event, and because I'm not going to, at this point, I'm not going to make you kind of remember all the different conventions here, but because this circle is solid, it means that we're actually also calling the superclass one. If it were in bold, if the line were thicker, then it meant that we were completely overriding it. Okay, so again, here we create the new entity and then we schedule this arrival with the right argument. So this is how we're going to do it. And again, and now the listener, now as we saw yesterday, we have two choices. We can use a listener or we can use an adapter. Now in this case, and which one should you use? If you are producing events that have exactly the right name and the right argument. Okay, so here we have arrival with an argument of an entity. Here we have arrival with an argument of an entity. Here we have arrival with an argument of an entity. So in those cases, we can just use a plain old listener. If the signatures are correct, but the name is different, then we need to use an adapter. Okay, but I won't go into that. All right, so that's, oops. That's what we had yesterday. And okay, let's get rid of that and let's go to the code. Okay, now can everybody see this?
Yes.
Okay, so let's start with the simple one, the entity arrival process. Again, we've done several instances of this. So entity arrival, and this you can pull this. This should be pushed to the GitLab. Okay, so we're extending arrival process. Again, that's what we're looking at is this. So we're extending the arrival process. And so for this, all we need to do is just implement this stuff down here. Again, that's the lazy method. And the lazy is is good. So what we again, we still need, if you remember from Java, we still need to write constructors. If we don't write a constructor, all we're going to get is the 0 argument constructor. So so what I've done here is this is another way. I mean, sometimes I call super, sometimes I'll call this and then just the setter. Again, it doesn't, this is just another way of doing it. The reason for this is something that I talked about in the Java class, that when you have multiple constructors, the best practice is to have one constructor that calls super and all the others call this. Now we've violated that a little bit occasionally, so, and it's not a big deal. It's more of a venal sin than a mortal sin, but still it's a good practice. So we're calling this here, and then even though this constructor is empty. Okay, so and then we need to make sure that we set our interarrival time generator. Okay, no problem. Now here's what we need to capture, and then see, and this is what I like about subclassing and why it's sort of lazy. So this is all we're implementing, and this is all that we need. Basically, there are 2 lines of executable code in this class. 2, count them. First, we call super, and the reason for that is because again, when we depict a subclass event with the same, the same thickness of line, it means that we are also calling the super class event for that. And that's how we do that. That's what we do here. And then, okay, and then I'm wrapping all this up in one call. I could have broken it up. So we're waiting delay for the arrival, delay of 0, and then I'm instantiating the entity right there. That's how I do it. So again, that's where this scheduling edge is being implemented. The other thing to notice is that here, notice that I don't even define this second arrival event in this component. That's actually legitimate because in this particular case, that event does nothing here. This event, the only purpose of this event is to be heard by some other component, that is heard by this component. Yeah, that's its only purpose. And if that's the case, SimKit is much more lenient than the Java virtual machine is about that. When it hears an arrival event, it's going to hear this arrival event with an entity argument, and it's going to look and say, I don't got one of those, but I'm going to send it to my listeners anyway. Okay, so now it doesn't hurt. It would not hurt. And if it will cause, oops. Okay, so writing this does absolutely nothing, and it doesn't hurt. So it can either be there or not be there in this particular case. So if for some reason what I've just been talking about is confusing, and it's less confusing to actually see this event in here, then by all means do that. Okay, so now let's do this entity server thing. Okay, so a lot of this we've done before. We have service time generator, total number of servers, we've seen that. Okay, so now our queue is going to be a sorted set containing entities. Okay, so that's something new. And again, notice the parameters are private, the state variables are protected. I got it right this time. Unfortunately, and this is NetBeans' fault, not yours. When you do a refactor, like if I were to refactor this and do the encapsulate fields things, see where it says fields visibility? If I were to actually do this, it would change this to private. I would have to change that to protected in order to make that right. So it is all too easy to flip your protected to private and your private to protected, and all of that is unfortunate. So it's unfortunately too easy to kind of mess that up. So it's worth just double checking. So parameters, and if NetBeans flips it on you, then flip it back. Okay, parameters are private, state variables are protected. Okay, and then here's our delay in queue and timing system, and we've done that for that previous one. So we're going to do exactly the same things here. So now, and this is the case that we saw before, where when I have a container that's a state variable, I will typically want to instantiate it in the 0 argument constructor. And the reason for that is, even though we have not typically used the 0 parameter constructor, there are situations in which it is the constructor that you want to use. And so we need to guarantee that this sorted set, this tree set, is always going to be instantiated. And one way to do that is to instantiate it in the 0 parameter constructor and then make sure that we call it. So again, we're calling this with from our bigger constructor. And that just guarantees that our state variable that's a container gets instantiated. And so this is fairly typical. We have our total number of servers, our service time generator. We do the setter for that. Now the run method has its initializations in the reset method. So that's the one thing that makes it special. We always call super reset. Why? They're just sort of bookkeeping things that happen in the super class. But we're going directly from the run event. We clear the queue, set S to K. D and W are not a number. So clear the queue. Number of available servers is, here I'm using the getter. You can use the getter or the variable, doesn't matter. Delay in queue, time and system, we initialize them to not a number. And the main reason for that is because what's the delay in the queue before anybody is delayed in the queue? It's meaningless. But how many are in the queue before anybody shows up? That's 0. That makes sense. How many available servers are there before anybody shows up? That's how many total servers we have. Again, that makes sense. Now remember, because the run event for this does not schedule anything, we don't put a wait delay in here. All we do is just firing the property change. Okay, so now let's look at our arrival event here. Okay, so we stamp the time and we add it to the queue. So as we've seen, state transitions require a bit more shuffling in SimKit. So let's see how we do that. So the arrival, the signature is entity. I'm calling it customer. Again, I can call it anything I want as long as I'm consistent. So I stamp the time. And then, as we've done before, I get the old value. Then I perform the state transition. I add it, and then I fire the property change. And then we've seen this before. So if there's an available server, then I schedule a start service with a high priority in this case. Okay, so let's look at the start services. So that's, that scheduling was the if S is bigger than 0, if number of available servers bigger than 0, the high priority here, that was the last argument, or the argument right after the delay time. Okay, now start service is a little more complicated. So let's see what's going on with that. So we want to make sure not to stamp the time again, because that would kind of mess things up. So we don't do that, but we need to pop the guy off the queue. So again, we get the old value, and then to implement pop, unfortunately, the sorted set does not give you a pop. It would be nice if it did, but it doesn't. And it doesn't even have something like a remove first, which it probably should, but it doesn't. So what we need to do is first get a reference to the first guy. It will tell us what the first one is, and then we have to remove that one. That's just the way they did it. It would have been nice if they put in pop, but they didn't. And then we fire the property change. And now we can compute the delay in the queue. So here it said elapsed and that was just short for elapsed time. So the delay in the queue is the elapsed time of this customer. That is the time between when this start service event for this customer, for this guy, where is it? For this guy, the difference between when it is now and when that guy had his time stamped. That's how long he's been in the queue. Now, the thing about these transient state variables like delay in queue is that they don't persist. In other words, this delay in queue, it's something where, okay, this customer showed up, it kind of boom occurs, and then basically it's kind of gone. So the old value doesn't really make any sense. So for these state variables, we just fire the property change with the new value. That's all we do. Okay, number of available servers, this is all familiar. Okay, now we schedule the end service with a service time generator, passing it the customer. Okay, and finally, now our end service has as its argument an entity of type customer. Just as we did with delay in queue, we can get the time in the system as the elapsed time of that customer, and then fire the property change, because time in system is also a transient state variable. So we just need the single argument one. Number of available servers, we increment. And then finally, if the queue, in the event graph, it said not queue.empty, but in the code, we have to say is empty. And so hopefully that won't drive anybody too crazy. Now, one important thing to note that I don't know if I did before, is that when we have a state, especially when we have a state variable that's a container, going back to, or if you remember in the Java class, we talked about when we have an array, or if we have a container as an instance variable, any setters and getters should use copies. And that's what we need to do here. So in other words, the generated NetBeans will generate get queue and just return queue, but that's not what we want. Because this is a set, we need to return a copy, and that's what this will do. So I actually have to write this code in. And that's that's important for debugging as well, because see what happens here when we put it in the queue, our get queue here, because this is going to return a copy. This is going to get the queue in the state it was right before we added this guy. And then when we add it and then fire the property change again, this will actually be the way the queue was before and the way the queue is now. And that will allow us to see exactly what the difference was. If we don't do that in our get queue, if our get queue simply returns, the variable itself without the other, whoops, what happened? Without the copy, then what'll happen is this old queue and the new queue will be exactly the same. And so what we'll see is we'll just see the new values in both places. That's what's going to happen. Okay,
Is
so
there a
that's,
reason that
yes.
priority high is done differently than the due arrival
Um,
on 109 or 154?
it looks the same to me. Yeah, so high priority. Why? Because there was a high priority here in the event graph. And since I mean, that's something that this is meant to kind of prevent an extremely rare situation. So it's I'm sorry, I'm not sure if I've addressed your question.
I thought you had to type priority dot high or something like that.
Great question. Yeah, so notice I didn't. Why? Because I had this import here. So how did I get that? All right, let's take that out. And now, okay, now I get a red squiggly. But if I get this, it says I can add an import for that. And what that import is, there it is right there. If you don't do that, you have to say just priority.high. That, you know, either way, they're both fine. Okay, so now running this is fairly straightforward. So again, I chose some uniform as the inter-arrival time generator, gamma as the service time generator. Okay, so here's my entity arrival process that I'm going to use. Here's my entity server. You know, all that's very straightforward. Here's where I hook them up as sim event listeners, because that works. This is a leftover from when I was debugging it. Okay, so now there's one new thing, I think. I don't know if I've talked about that before, but for the, well, let's look. We've used simple stats time varying for the time varying statistics, like number of available servers. That's what we use that for. The delays in queue and time in system, those are tally variables. Remember from the first written assignment, those were actually computed differently. You added them up and divided by the number. That's what a tally does. So a simple stats tally uses that as the logic for computing the averages. And then the new one is this one called collection size time varying stats. What is that? What that does is that's listening for Q, but remember Q, the property change for Q is a sorted set. So what this does, the collection size says, okay, I'm going to hear some kind of collection, but every collection has a size. So what I'm going to do is I'm going to collect the time varying average of the size of this collection that I've heard. Okay, so then I add them all as property change listeners, I stop at the time, etc. And so now what I can do, okay, let's run this and I'll show you what I can do now. And since we're running out of time, you'll have to look at it and figure some of this out for yourself. Again, I always do the print lines of the objects to verify that they're getting the parameters I thought. 100,000 is my latest favorite stopping time. Okay, so I see that there have been this many arrivals, this many serves, so there are 3 in the system. So, and as a double check, I could also see whether when it finished, okay, if there are 3 in the system, what should it look like? There should be 2 in service and 1 in the queue. Okay, I'm not going to go there, but just based upon the things we were collecting, the average number in the queue is here, the average delay in the queue, the average time in the system. Okay, so those are all out there. But then because we've computed the average delay in the queue and the time in the system explicitly, we can now try to see how Little's formula is doing. So I can compute the arrival rate. Okay, where do I do that? I do that right here. So remember, my arrival process had a state variable number of arrivals. So that over the sim time is the arrival process, the arrival rate. So, and I can compute the utilization. Again, we sort of did that. But now I can look at the number in the queue stat, the mean of the number in the queue divided by the arrival rate. And that's what Little's formula says should be the average delay in the queue. And likewise, the average number in the system, which is the average number in the queue plus the total number of servers minus the average number of available servers, all divided by the arrival rate. And that's the Little's formula version of the average time in the system. And we see here, so the average delay in the queue according to Little is 24.7622 versus 24.7626. The average time in the system, 28.8080 versus, I'm sorry, 27.8080 versus 27.8092. Very, very close. They're not exact. Why? Because there were still 3 in the queue, in the system.